So I'm going to talk to you about this integrated research infrastructure effort. It's a little bit tangential to what you've been talking about for the past few days. You're talking about machines we have at ALCF, how to get the most performance out of them with your mod sim applications and AI. What we've been looking at with integrated research infrastructure is more how these systems can be used for experimental science across the Department of Energy facilities. So what we'll talk about is essentially ALCF support of experimental scientific computing, which is we've been doing for a long time at ALCF, and then the integrated research infrastructure effort at DOE, and then Argonne NEXUS, which is our effort in the IRI space here at Argonne. If you look at the evolution of systems at ALCF over time, you'll see we've been on a long road. If you look at the systems on the left, they look actually ridiculously small given today's perspective, but we've been at this for a long time. And so you see this progression. And while we've been going through upgrades, you see a most recent upgrade to Aurora on the right side. DOE operates 28 user facilities. ALCF is a user facility. The other computing facilities are also user facilities, but there are 24 other user facilities that are operated by DOE, and some of them have undergone upgrades over time, similar to what the trajectory that we've been on, to upgrade what they can do, the science that they can do. They're producing more data, and they need more computing to process that data. If you think about them going through their upgrades in terms of their scientific apparatuses, they may not also upgrade the computing at their facilities to correspond to their increased data rates, so they need more computing. So at ALCF, we have done this for a long time. We have worked with experimental facilities going back well beyond the examples that you see here, but I'll talk through these a little bit anyway. Going back to 2015, we were looking at how to integrate with high energy physics, the ATLAS experiment, to run their workflows on our systems. This goes all the way back to MIRA at the time. We're running at the scale of all MIRA generating events for the ATLAS experiment. With Fusion, we worked with them while their experiment was ongoing, and they collect data. We move the data to ALCF, analyze it, send the results back to the D3D facility in California. And then also with HEP, with the LSST desk project. You might say, yes, that one is getting first light next year, maybe, right? So how were we working with them 7 and 6 years ago? The answer is that well before the telescope was even being designed, they're simulating images that would come off the telescope so that they could build up the analysis pipeline. So the analysis pipeline would be ready when the telescope actually began operation, which again, will be next year. We worked with LIGO in terms of multi-messenger astronomy, coupling signals that we get from, say, LIGO and telescopes when we have gravitational wave events. On the left, you see an effort to take electron microscopy data of mouse brain and reconstruct it. We've been working with this project for quite some time. Again, with Fusion, now we move into the time where AI is starting to kick up, and using AI to understand and control the shape of the plasma. Work with BES in the light sources, for light sources across the country, and they've all gone through upgrades and need more computing. And so we have worked with them to take their data as it comes off the beamline, move it to ALCF, compute on it, and send those results back. And then SBND we've been working with also for some time, and continues today. I mentioned the fusion example. So this is just a little bit more depth on that fusion example. So when they run those experiments, they have a shot, an experimental shot every 20 minutes. And in between those shots, they want to take that data, run analyses on it, understand what configuration changes they should make for the next shot. And that involves gathering the data, running analysis, having discussion among the scientists in the control room at the facility, and then applying that configuration within that 20-minute window. You can see on the bottom right the approach that they originally took, which was they have the shot, and then they run the analysis, and the analysis would take longer than the 20 minutes that they had in between shots. And so what they derived from one shot could only be applied in not the next shot, but the one after that one. And so we worked with them to take that data, move it to ALCF, run the analysis, push it back to them. You see in the bottom right that we were able to run that analysis much faster. And so the results got back to them, and then every shot was informed by the analysis results instead of every other one. In addition to that, because we had more computing here, we said, well, can we run higher resolution analysis? And so we also ran a 16 times higher resolution analysis and provided those results to them. We ran this throughout experiments that they had reservations on our system. And so the whole week during that experiment, they were able to get the benefit of these analyses. That was just a blow up of the shots so that you could see that. I mentioned working with light sources. So at the same time we were working with the fusion group, we were also looking at what is the future of analysis from the light sources. And so they conveniently, 3 of the light sources were running the same sorts of experiments at their beamlines using similar or the same codes. And again, looking at how they could leverage the ALCF for their work. We ran this test where we took one of their largest data sets, and then over the course of 2 days continuously, this is how beamline allocations are usually done at the light sources, is that you get 2 or 3 days at the light source to run your experiment. They work day and night and gather data. And so we took one of the largest data sets that they gave us out of like 100,000 data sets, and we transferred that data set from APS and ALS to the ALCF and analyzed it and sent those results back. And what you see on the bottom are plots of the throughput. So as we brought tasks in and ran them, were we able to keep up with that? And you see mostly that's true. This was a really good experiment for us because it showed that despite being a remote facility and some of the largest data sets that they have ever worked with, we were able to keep up with their experiment over the course of 2 days, which is again, a simulation of their real world analyses. And also NSLS2 on the right. So it was 3 different light sources. We also did another experiment where we looked at now going from multiple light sources simultaneously to 3 compute facilities. The first one was from 3 light sources to ALCF. In this case, we were going from 2 light sources to 3 compute facilities. You look at the names of the machines on this slide, and you can see this is kind of old because you don't actually recognize the names of the machines. Theta has been decommissioned, and Summit is about to be decommissioned, and Corey is gone. But again, the point here is that we could leverage the computing facilities even if the light sources were operating simultaneously and keep up with their workloads. So we were working with the experimental facilities to achieve this because we anticipated that they would need this kind of functionality. At the same time, there was an acknowledgement from DOE that this sort of thing would become common among many of the 24 user facilities that DOE operates. And so this integrated research infrastructure effort was launched. In this case, we have multiple different activities, but for this report in particular, we gathered like 160 scientists across the DOE facilities and tried to understand all of their requirements and what we would need to do to actually satisfy their needs. This report was published last year. No surprises, right? If you look at the center column, the themes turned out to be that people needed to handle their data quickly at experiment time. They had large data-intensive workloads, and they wanted to preserve their data over time. So there's long-term campaigns where they want to store the data and be able to go back to it. In general, they want to do that, but especially now thinking about the impact of large data on AI, of course they want to do that. So the intent was, and this is from an earlier white paper from the IRI effort, the intent was that if you had an experimental facility that wanted to use a facility like ALCF, they would sit down and do that and work on all of the individual aspects to make that work. So they would have an integration with the facility. And then if they wanted to go to a second computing facility like Oak Ridge, they would have to go through all of that work again. So very standard approach here for anybody who works in software, like all of you. You have to have some kind of an abstraction layer. So rather than in the top diagram, having each experimental facility make a custom integration with each computing facility, they should be able to do that one time according to some interface and get access to all of the computing facilities. And then, of course, that would compound because all the experimental facilities would do this the same way. This is a slide from the facilities program manager at DOE, Ben Brown. It's kind of his vision for how this should look. The thing I like about this slide is, I mean, I wouldn't have made this slide this way, but I appreciate the way he made it because I would have put the computing centers at the center of the diagram because, of course, that's where all the computing happens, right? All the data comes from the experimental facilities into the computing facilities and then goes back to them. It seems like a natural layout to me. But his point was researchers are at the middle of all of this. They're the ones who are doing the work. They're the ones who are being enabled by this. And so I just like to point that out. But you see it's sort of an assembly of all of these pieces and the things that this would enable. So that's, I talked about our early work at ALCF with experimental facilities. I talked about the DOE project. Then along the way, we thought about, ALCF thought about, how do we express that at ALCF so that it's usable, and how can we make this easier? The goals are really, again, to simplify access to the Polaris and to Aurora, and to automate this data transfer and workflows, and to provide generalizable solutions so that it's easier for users, and support some means of interactive introspection, and publish data and support publishing data. There are certainly communities that generate a lot of data and then keep it and nobody looks at it but them, only within their communities. There are other communities where they manage a worldwide consortium and they all need access to all 10 petabytes of the data that's stored at the facility. So to figure out how we can make that work for them. So this NEXUS initiative at Argonne aims to achieve these things by a number of services or facilities that we're deploying. One is that on Polaris, we have an on-demand queue. So there are jobs that experimental facilities need to run. They need to run them rather urgently. This is the time-sensitive theme that came up earlier. And they need those computing nodes when they need them. And so the way we balance that is we dedicate some nodes to this on-demand queue. And there's an accompanying queue called a preemptible queue. And so you can run in a preemptible queue knowing that your jobs might get vacated at any time. And they get vacated when users put jobs in the demand queue. So really, jobs go in the demand queue and other jobs are kicked out almost immediately to make room for those on-demand jobs to run. 56 of the nodes on Polaris are dedicated in this way. We have created service accounts. So you all have your own accounts. If you worked as part of an experiment, then you might have a service account, which is accessible to you and your counterparts on your experiment. And the point of that is, again, if you go back to the light source example, you have people who are working for 48 or 72 hours continuously running experiments, and they need to be able to access the details of their data and their analysis as some of them go off and go to sleep and other people come in to run the experiments. This shared service account gives them a way of doing this and is also used for automating the data transfers and the workflows. I'm sure you've heard of the Eagle file system while you're learning about Polaris. We have deployed on Eagle this Globus sharing technology or Globus collections, which allows you to take parts of the data that you have stored in the file system and share it with other users. Those can be people who have ALCF accounts. It can be people who don't have ALCF accounts. They just need a Globus account, and you can make that data publicly available. We're using, I mentioned now Globus multiple times. We're using Globus infrastructure to achieve this. You're probably familiar with Globus transfer, but Globus has been developing tools for workflows. You could go back to things like Parcel, or you may have heard of FunkX, but these tools are being rolled into a larger sort of a services offering where in addition to the transfers now you can run workflows and automate them. We have something called ACDC, this ALCF Community Data Cooperative. And the point is that, again, the data that you have available, you could share it, but you can also decorate it with metadata that makes it easier for you and your community to find, and then download or have some integrated analyses directly in ACDC. You can find that at acdcalcf.anl.gov. And then we've also been working with projects to build dedicated web applications. The point here, again, is not that we should write one-off applications per science area, but ideally that there would be some themes and some infrastructure that we could develop in there so that it would be transferable or generalizable. So one of those is, for example, a site for sharing and analyzing cosmology simulation data, which I'll show, that'll come up again later. So what does this look like? So for the light sources, again, we have this, this approach that the way it works is that they have this APS-DM, the data management system, that collects data during the experiments. And as a data set is collected, as that data set is closed and becomes available, it's automatically shipped from APS to ALCF. And that analysis job shows up in Polaris in the demand queue. This leverages the service account. And then the job runs and the results are pushed. They're made available on the Eagle file system. Also can be pushed back to APS for them to view on the beamline during the experiment. The important thing I would want to point out here is that in terms of the service account, what this means is that the APS operates very similar to ALCF in terms of users, right? We have users on the system. They have users who apply for beamline time and come there and do their experiments. But if they want to use ALCF, they don't need to get an ALCF account. Because everything is internalized into this data management system, the users don't touch it. The users can't access ALCF themselves. It's all automated and it's buffered away from them so that we don't have to create accounts for every APS user who shows up, and they get the benefit of this functionality. I think I will not talk through this slide in detail, but the point is that this is how we bootstrap what I was just describing. So you have some one-time setup at the beginning where you have to build, request a service account, get this integrated, get your application flow in place. And then once that's in place, you have this basically just running by itself. And now this is a diagram showing the APS. There are 68 beam lines. And so if I talk about enabling the APS to do this sort of thing, you might think, okay, we've enabled one experimental facility, but it's actually that we've enabled many sectors around the APS. And so they're all individual experiments that have this similar need for functionality. And so already we've I should update this slide because now there are several more beam lines that have been added, and we expect this to just continue. This now becomes maybe a little bit hard to see, but this is just what the Globus tools enable for us is that we can compute, we can transfer. Auth is bundled into the Globus tools again, so that's simpler. The flows orchestrate things, and there are UIs for monitoring this flow. The UIs are, I'm more of a command line guy myself, but there are communities that really want to be able to see what's happening with we've automated their workflows, and they need to be able to track them. Some people will say, they have a better interface to their banking system than they have to their science. And I think, well, okay, that shouldn't be true. We should actually be able to support them the same way. So this is a point of that. And on the right, what you're seeing is just from the bottom up, just a representation of the steps that this flow went through. I did talk through a fusion example earlier, and that one was rather old. And so we've been working to update that. And so now talking with D3D, the fusion facility in San Diego, they want to take this into production with new applications, with multiple applications that they run in between their experimental shots. And they need to be able to do this with some redundancy. So they can run at ALCF, but if ALCF is in maintenance or having an outage for some reason or is busy, I mentioned having a demand queue. There are only so many nodes in the demand queue. They might also want to be able to use the other computing facilities. And so we're working with them to do this same thing, not only at ALCF, but at NERSC and at OLCF, and have demonstrated this is successful, but we're continuing to work with them to get it to a production level so that they can rely on it during experiments. Very close. One of the other projects that has been identified within DOE as a priority is the ESGF2 project. So in this case, they have, 8 petabytes of data actually originated at Livermore, now it's replicated at ALCF and at OLCF. And to enable them to analyze that data, we have put together an environment where they can search for the data locate where it is, and then run an analysis on it. When I say search, this is really a very much an ESGF side thing that they want to do, right? I mean, they're searching for environmental data for a particular analysis that they're doing, and they get back the results, and then they choose the results that they want. They can resolve that to a particular location, again, ALCF or OLCF, and then choose an analysis to run. And it might be that we take the compute to the data, we run the analysis where the data resides. It might be that we move the data someplace else, because that's actually a faster way to get their analysis through. I mentioned earlier, the sort of some communities have a worldwide consortium that they're operating with, and this is really the example that I had in mind. So when I've been talking about computing, I'm talking about ALCF and OLCF, but the ESGF project is really worldwide. There are people all over who will leverage this, and maybe our approach then will extend to the same things that they're doing in other countries. And I mentioned AC/DC, so this is just a screenshot of AC/DC. The point here is just that having your data on a file system makes it accessible to you. Sharing it with a Globus collection makes it accessible to other people, but doesn't always make it conveniently findable. And so some way of capturing metadata that allows you to search and find what you're looking for in your data is enabled by AC/DC. So if this is of interest to you, we could work with you to expose your data here. We're still working on developing this. Yeah. And then I mentioned in the custom web applications space, I mentioned a cosmology simulation app. So in this case, we built a portal where you could go and search for data using various cosmology parameters. We have hundreds of terabytes of data stored here. If a community wants to access it, in this case, they would down select to some more reasonable size and transfer only that data over Globus to their institution. Again, they don't require an ALCF account. They can just make that transfer. Maybe they've gotten to a point where they're only transferring tens of gigabytes or something, and so that it's reasonable for them to transfer it and analyze it. But we recognize that that's not always the case. And so now we're working with the hack team to extend this approach so that on top of selecting the data that they want to analyze, they can also run those analyses on ALCF systems. This may look different than the other examples because it's not an experimental project, but it is similar to the ESGF project because they have a lot of data. We have hundreds of terabytes in this case, but they have petabytes stored on our file systems. And making that available to the cosmology community for analysis without them requiring accounts on the ALCF systems is leveraging many of the same NEXUS capabilities that I was describing. And in the interest of keeping your lunchtime talk short, I'll just end by saying, if this seems interesting to you, you can find this report. We've done a lot of work in the IRI effort across DOE computing facilities and across experimental facilities over the past several years. So the report contains a lot of that material, but really the meat of the report is the first 20 pages or something that summarizes all of that work. So I think it's a fairly short report to digest if you look only at that initial content. Any questions?
What kind of computational resources that each of these 24 labs will require don't require that much. You want so my question is, how much resources does each of these 24 facility require? If they don't require too much, then they can actually do it themselves using their own computers. If they require a lot, then you have a scheduling problem when all 24 of them trying to get on the ALCF resources at the same time.
Definitely true. So there are a lot of different ways to answer that question. So I'll give you several answers. One is that at one point we were talking with one of the light sources, and they said that they had experiments that while they were running, they would require 1.5 exaflops of sustained computing. And we said, you're not going to get that. They've since been able to pull that back in with some improvements to their code. So they now have a more reasonable demand for their computing at experiment time. Also, your point about if many of them have moderate needs, but they have them at the same time, then we also run into a problem of maybe oversubscription of our resources, right? And that's true. It might mean that we need more computing at the computing facilities, which is what we do. So probably that would be the answer. We have to think about the aspect of balancing compute across the facilities is important. And so making it easy for them to access all of them so that they can run their codes on Intel hardware at ALCF or AMD hardware at OLCF is a challenge that they would have to come up with. And I put up this slide of 24 facilities. Certainly the demands across them are a distribution, right? Some of them will only use local resources because their demands aren't that great. Some of them will use the higher end resources because they need a lot. In that second group, you can imagine them doing different types of work. Some of them being more compute intensive, more data intensive that they would need to run at places like this. And some of them being less compute intensive in that they can run locally. And so there's a bit of a challenge in there for either for us in IRI or for them in the experimental facilities to think about automating that part of the work, right? To say, we brought the data in and now we need to run multiple analyses and we'll push the compute intensive one off remotely and do this one locally and then bring them back and merge them together to get the result we need on the timeline that we need. But it's exactly all of those things that are challenges for us.
Any other questions? I got a question. How long is the full report or the full integrated research architecture blueprint and activity? You said the first 20 pages is a good summary. Is it super long if you want to read the whole thing?
I would estimate that there's another 40 so pages in the report that are background material. So
not too bad. Not too bad.
The appendices are 2x the real meat of the report.
All right. Let's thank the speaker again.
Thank you.